All right, thanks everyone for coming to the ECE Colloquium series. I have the great pleasure to introduce Michael Jordan. I'm not sure how much of an introduction Professor Jordan needs, as he's a well-recognized pillar in our community. So I'll just briefly comment on some of the many accolades he has received during his career. Professor Jordan is a member of several prestigious academies, including the National Academy of Sciences and the National Academy of Engineering. And he's a fellow in many of the top societies spanning multiple fields and disciplines, which this is pretty impressive. So IEEE, SIAM, ACM, AAAI, amongst others. And of course, he's received many honors and awards, including most recently the Ulf Grenander Prize from the American Mathematical Society in 2021, and the IEEE John von Neumann Medal in 2020. So beyond this, Professor Jordan has many publications, and his work has influenced not only the direction of many fields, including stats, optimization, and machine learning, but also impressively the emergence of new fields. So I have to say his ability to recognize precisely the right time for two fields to merge into a new interdisciplinary field is arguably unmatched and profoundly important for the future of science. And so at present, we're witnessing the emergence of an entirely new field at the intersection of machine learning and economics and control and dynamical systems, of which Professor Jordan is a primary mover. So I hope we hear some of his perspective on this in today's talk. And so without further ado, I'll turn it over to Professor Jordan.
All right. Thanks, Lily. It's been a pleasure to get to know you a little bit because you're a leader already in this emerging new discipline. And so I've learned already a lot from you. And it is a small crowd of people that are seeing that statistics, computation, dynamical systems, and econ are all kind of, the three of them need to come together, not just pairwise. And you've already been there. So let me share a screen and get started on this. I do have quite a bit I want to tell you about today. So hopefully you can see the screen. If not, let me know. All right, so it's my pleasure to be in the University of Washington today, all the way from Italy. Probably some of you are also abroad somewhere. It's quite a world we're living in now. So you see in the title there's a lot of buzzwords. I do want to talk about computation and economics and a little bit about statistical inference as well. Let me start by giving a little perspective on why I'm doing this. It's driven by real world thinking and real world problems and spending time in industry as well. So machine learning is a terminology that's been around for a few decades now. But when I was first exposed to it, I really was puzzled about what was new in it, because it felt like statistics and it felt like a blend of statistics and computer science. And I still believe that's true, but it's just been a discipline that's taken the fundamental ideas in those fields and built an engineering field on top of that. So I think this is not dissimilar to what happened to, say, chemical engineering that emerged from chemistry and quantum mechanics and fluid flows and so on. There were fundamental scientific ideas, but that whole new field had to merge to make this into something real world. So in developing a real world discipline, machine learning has focused on two sides. One of them is the pattern recognition side, and the other is the decision-making side. The last 10 years has been dominated by pattern recognition. So gradient descent and large parameter systems of large amounts of data. And it's become a commodity because of platforms that exist to make it easy. So much so that people have argued that pattern recognition is sort of everything, that if you can predict and find patterns in data, that's kind of the main part of the problem. So what I argue today is I don't believe that's true, that decision-making has its own complexities. In fact, we are really only beginning to touch some of those complexities. And these particularly come out when you think about high-stakes decisions and sets of decisions in various kinds of configurations. So let me say this in a slightly different way, less academically. So I really do think this is a emergence of a new engineering field. Therefore, it must exist in the real world outside of academia. And I think that's definitely been true. So this is my short history of machine learning as a really outward-facing discipline. So the first generation, I would argue, was already in the 1990s, where you saw companies like Amazon and others in the back end of the company, where you were doing things like fraud detection or search or supply chain management. You saw that essentially machine learning. You saw large numbers of computers. You saw huge data sets to be able to do things like find fraud at levels that made e-commerce possible. And even more importantly, supply chain management done with billions of products and hundreds of millions of people. So this was algorithms that were akin to the ones we see today. They were mostly random forests for Amazon, but they were neural nets for others. And so in some sense, not that much has changed. But I do think there's been epochs. The second generation, in my view, is one where you started to see recognition that this was a data often about humans, not just about supply chains and so on, fraud. So commerce and transactional kind of data led to a focus on human-related data. So recommendation systems emerged in that era. So I think the first and second generation led to billion-dollar industries, and really was a meaningful thing in the real world. The third generation is what I'm going to call the pattern recognition era. The data is now not just about humans; it's kind of coming from humans. So speech data, vision data, natural language data. But the same ideas were being used: gradient descent and pattern recognition systems and large data sets and cloud computing. But it just all got bigger and faster and in some ways more impressive. But really, it's just taking data from humans and seeming like it's mimicking human intelligence. So the AI buzzword started to get used in the third generation, I think inappropriately. I think actually the fourth generation is already emerging, and I think it's even more interesting than classical AI goal of mimicking a human being. It's the emergence of markets that are planetary in scale, involve huge numbers of interactions between humans and machines, data flows, values of data, and all kinds of unsolved problems. All right, so let me talk a little bit more about decision making. It is less of a focus than pattern recognition, but I think it's equally important, probably if not more important. So the example I like to use to think this through a bit is think about medical decision making. Imagine you've gone to the doctor and the doctor's measured all kinds of things about your body, and also maybe figured out your genome. And so there's a 100,000 dimensional feature vector which goes into a large machine learning system, say a big neural network, which has been trained on all the world's medical data. So in a few years, that's something like that may happen. And let's suppose that one of the outputs of that network is a prediction about whether you're about ready to have a heart attack or not. And so based on the historical data, maybe 0.7 is a value that is a threshold for that prediction. So suppose your number is 0.701. Are you going to treat that as a decision? And the answer is no. It's going to be the onset of a dialogue with the doctor and with the system. You're going to ask questions. First of all, what's the error bar on that 0.701? And not just a Gaussian error bar of some kind, but an error bar means the uncertainty that you have in that prediction. And uncertainty arises for all kinds of factors, including what was the data set used to make the prediction? Is it related to the data that was used? Is it related to me? Is it the same population of people? Have machines changed in some way? Because we're going to be building systems that are working over many years, not just over a day or two. And so all of these provenance issues about data are going to affect the error. Now, you're also going to start asking counterfactuals. Now that you might have a heart attack, you might say, well, did you know certain facts about me? Or what if I were to exercise more? And you're going to have a dialogue about things that you thought of only in the moment. So you now realize that that neural net didn't have all the world's medical data, in the sense of having data that's relevant to the decision at the moment. And that's always going to be the case for consequential decision making. You're going to think it through in the moment, and you're going to want to ask counterfactual questions. You're going to retrain the network in a different way to reflect a different way of thinking about the decision you're about ready to make. And this is what you do with a real doctor. You think things through, you bounce them back and forth, you start to develop trust in the doctor because of what's coming out, and so on and so forth. Now, that's just one decision. We never make just one decision. We make sets of decisions typically, and they are often at different time scales, asynchronous. During the day, you'll think about all kinds of decisions you have to make. And it's not just a single person. It's often across a network of related people or even non-related people. Think about the pandemic response. Worldwide, we're making decisions about people's health, and it's all interrelated based on data flows coming, at all manner of locations and timeframes. And now, even more importantly, we started making decisions in the real world that interact. You're going to have scarcity. You're going to have real world congestion. You're going to have other kinds of relationships among decisions. And now you start to have an economic perspective on decision making. All right, so I could go on, but hopefully you get a little of the spirit. Let me dig in a little bit more with a kind of another thought experiment. So recommendation systems, you all know what they are. They're a pattern recognition system. They find patterns in purchase data and cluster people or products so you can make other recommendations to people. So they're used in essence as decision tools or decision making systems. But that's not a very useful perspective for real world domains where you can have things like scarcity. So if you think about where recommendation systems arose, it was for things like books and movies. Those are things that where there's not much scarcity. In fact, movies, you can copy the bits as many times as you want. So really there is no scarcity. And I think seductively people who built these systems just thought we have to worry about scarcity. We're in the computer world where we can copy things as much as we want. But in the real world, you can't do that. So if you're starting recommending restaurants to people and everybody in a certain city is using your app, then you're going to recommend too many people to go to a given restaurant. Maybe 100 people are recommended to go to a certain restaurant. You've created congestion. And if you think about how to fix this now, then you start to see that the pattern recognition perspective is going to lead you astray. And so I think in Silicon Valley, people think that you're going to top down decide what to give people. You're going to decide who gets to go to what restaurant or who gets to go down what street based on what you know about them. So you know their whole browsing history and you're going to infer things about them. So this is kind of the perspective of companies that advertise. They try to figure out things about their customers and then make decisions for them. And that's really not the right way to think. We don't know in the moment what we really want. What restaurant do I want to go to? It depends on all kinds of factors that I'm only thinking about in that moment. There's no way the browser is going to know about my decision making in that moment. I really want to be like when I walk into a market and I'm going to think through the options and I'm going to make decisions in the moment. Same thing about going down streets and making decisions about how much in a hurry I'm in today, how much would I be willing to pay for going in a faster route, and so on and so forth. So you can sort of see here that it's machine learning blended with markets. That's really the system that we want to think about. So if you create a market via data analysis, then you're going to connect producers to consumers, perhaps. The restaurant is going to know about the people who want to eat in that restaurant, know about all the people who are available. The diners are going to know about the restaurants that are available, and there's going to be an exchange of information based on their past history, something like a recommendation system, but now in the context of a two-sided market. And this isn't just classical microeconomics. In microeconomics, you would have a game or a matching market, and you would assume you know the preferences a priori and then do some kind of a matching. Or you would use historical data in some way, perhaps, to form preferences. But if you think about restaurants and diners, if I go to Shanghai, I've never been to Shanghai, perhaps, and so I don't know my preferences for the restaurants. But there is a history of my dining activity, and somehow, like in a recommendation system, that should be brought to bear in making this market an efficient market. So there really needs to be a deep blend to build systems that actually work in practice, that don't create congestion and bring value to people. Let me just say that there's not that much new in this perspective. Certainly already in the 1950s, people like David Blackwell were doing statistics, economics, and algorithms simultaneously. And his approach has been rediscovered by many in many fields, but it really has kind of disappeared to some degree. Blackwell was rare. You have pairwise connections between statistics and economics. That's econometrics. Between statistics and computer science, that's machine learning. And between economics and computer science, that's algorithmic game theory. But you rarely have all three coming together. And again, Lillian and others are a counterexample. There is an emerging kind of appreciation for really deeply trying to blend these fields again, a la Blackwell. And let me just say that if you're an algorithmic game theorist, you already kind of think about algorithms and markets together. Markets are algorithms. So in fact, if you're an AI person thinking about how to build intelligent systems, part of the intelligence comes from market behavior. The individual agents don't have to be very intelligent if somehow the market makes them overall more intelligent. And somehow AI, there's not enough awareness of that, especially the people who do learning systems. Learning is supposed to solve the problem, but it doesn't. Markets and learning can help to solve the problem. All right, so there are many, many problems that are really exciting and interesting, and many of them unsolved at this interface. I am going to talk a little bit about exploring and exploration-exploitation trade-offs, like we look at in learning, and what happens when you bring that perspective into markets. Also, as I've already alluded to, recommendation systems blended with markets. There's lots of interesting information and signaling problems that arise there, and then all kinds of other sorts of problems. So let me jump into a particular concrete project that helps to frame some of my own thinking about this, that leads to some follow-up work, and just to also kind of give a flavor of something concrete. So this is work with Lydia Liu and Horia Mania, who've been graduate students with me at Berkeley. And we're bringing together two ideas in this project. One of them is a core learning problem, multi-arm bandit. You really don't get more core than that. You have a set of actions and you don't know which is the best. So you try them all out in some way, in some protocol, and figure out which one is best, and then try to choose that again and again. So that's a good classical learning problem. And on the microeconomic side, we're going to talk about matching markets. We've already talked about that a bit in the so far. All right, so multi-arm bandit, hopefully not much review is needed. Have an agent, which is trying to decide which of a number of actions it prefers. Associated with each action is a reward distribution, which is unknown to the agent. So they pick an arm and they get a sample from the reward distribution. And there are many algorithms that aim to find the best action, or and perhaps find actions that give high reward over time. One of them, which is achieves a good regret, i.e. the reward it achieves compared to an oracle that knows the best arm a priori. That regret is logarithmic. That algorithm is called the upper confidence bound algorithm. So what you do is you simply form a confidence interval for each one of the reward distributions, where you're forming a confidence for the mean of the reward distribution. And the algorithm picks the arm which has the upper confidence bound, which mean largest. So that's a good idea for 2 points of view. One of them is that the upper confidence will be high if the entire distribution is shifted up to the right. I mean, it's a good arm to pick for the exploitation point of view. Or it could be that it has a very large confidence interval. Therefore, you should explore that arm and see what the real mean reward is. Perhaps it is not so high after all. So the UCB algorithm picks the upper confidence bound and then continues to update the confidence bounds. All right, so that algorithm is known to achieve logarithmic regret. And what we're going to do is blend that with a matching market. All right, so matching markets, again, hopefully all of you know what this is. It's a two-sided market. You have buyers on one side, sellers on the other. And classically, you assume that the preferences are known on both sides of the market. So buyers prefer the sellers, and sellers have preferences on the buyers. And then algorithms exist, for example, the Gale-Shapley algorithm, which iteratively form links between the buyers and sellers, and do so in a way that you obtain a stable matching, that no pair wants to switch with some other pair. All right, so obviously we're going to try to put these two ideas together. What if we have a matching market in which the agents don't know their preferences a priori, and in fact on the other side of the market the arms have preferences back on the agents which are not known a priori either. So we need to have an exploitation solution to this problem, where on both sides of the market, they're exploring their possibilities and a match is being formed as you explore. So we may have two agents, like in this diagram, the bear and the human. And the interesting question is what happens when they both pick the same arm? So in our model, we have a competition at this point, and that is arranged by having one of the agents get a reward and the other gets no reward. So which agent gets the reward? Well, it's determined by the preferences on the arms side of the market. So the human from this point of view is looking at this situation, realizing they liked arm 2, but the bear seems to like arm 2 as well. And so, but the bear was the one who got the reward. So the human realizes maybe I should explore some of the other arms more than I otherwise would, because I'm losing to the bear when I pick arm 2. So the human needs to explore more than he or she otherwise would. That's going to be bad for regret. You're going to have to pay a higher regret because of the presence of the other agent in the game. So the question is, how much more regret? Is it worse than logarithmic? And what we have to do some theory to establish that. So here, the basic setup is, again, this notion of a bandit market, agents on one side, arms on the other. You're learning your preferences. And you have to define a notion of regret. Just briefly, the basic idea is that we take the total reward that an agent has relative to an oracle who knows the preferences a priori and runs the Gale-Shapley algorithm. So we call that a stable regret. And so here's one of the algorithms we've actually analyzed to get an upper bound on the regret. This is a simple blend of Gale-Shapley and UCB. You form upper confidence bounds, which you update over time, and you give the upper confidence bound to the Gale-Shapley matching algorithm instead of the mean reward. Okay. And if you run that algorithm and now do the analysis, you can prove that it has logarithmic regret. So you do not lose the logarithm. And where the overlap comes in is in the denominator term. There's a constant there, delta squared, and that is a reward gap between the agents. So we're used to seeing reward gaps for a single agent between the different arms. We still have that, but we also have overlap between agents. So if the bear and I both like the same arm, then we're going to have a small reward gap, therefore a higher regret, but it's only in the constant term. All right, so there's lots more to do with this problem. As you see at the very bottom there, I say something about incentive compatibility. It turns out this algorithm is incentive compatible in a certain sense, but there's much more to do along the lines of real game theoretic analysis of the algorithm. That we have a decentralized version of this algorithm, which we've been working on recently, and there's much more to do with large-scale problems and information sharing and signaling, and we also could consider cases where reward distributions are the same or different. There's just a whole playground to work in here. Having done that piece of work, we were motivated to look at UCB for other problems, including the classical reinforcement learning problem. Surprisingly, much of the work in reinforcement learning has not involved exploration-exploitation trade-offs. Even though reinforcement learning emerged from bandit algorithms originally, somewhere along the way, exploration-exploitation was sort of dropped and people focused only on maximized reward. So with Qi Zhen, Ziyana Zhu, and Sebastian Bubeck, we investigated adding UCB to Q-learning, one of the classical algorithms in reinforcement learning. So I just want to briefly mention this. You probably all know what reinforcement learning is. It's a Markov decision problem. It's like bandit learning, except there's also a state, which is updated over time. And there is a debate in the literature whether to prefer model-based reinforcement learning or model-free. Model-based is where you form a transition model for the dynamics from data, and you update the model and then run an algorithm on the model, maybe a dynamic programming algorithm. And the alternative is a model-free approach, more like bandit learning, where you're simply choosing out actions and seeing which gives the highest reward. Okay, so from a theoretical point of view, you want to sort of see which is best. And we're going to do this in the context of having exploration as part of the procedure, which again has not been the case for much of the theory work in reinforcement learning. All right, so when we add exploration to Q-learning, here is the Q-learning algorithm. And again, I'm not getting into details here, but many of you will know this algorithm. In blue, you see it's a simple kind of Bellman update. And we've added a term B sub t, which is this exploration term. It's an upper confidence bound. And B sub t, you can see at the bottom of the page, scales in a particular way. All right, so we have an algorithm now which has exploration embedded in the algorithm. We can analyze how well it does. So on one page here, I have the state of the theory of reinforcement learning when you have exploration as well. At the top of the page, you see the model-based paradigm, and there's been already substantial work on the theory for model-based paradigm. And you can see the regret is scales as square root of t, where t is the number of time steps that the algorithm runs. And so the question has been whether or not for the model-free paradigm, it's worse than square root of t. And early work seemed to suggest it was. If you run Q-learning with an epsilon greedy search, meaning that from time to time you simply toss a coin and you decide to choose a random action instead of the optimized action, then you pay you have a bad dependence on t. Okay, it's linear in t. And there's another procedure called delay Q-learning, which has a t to the 4/5 regret. But if you, what we were able to show in this paper is that if you include UCB into Q-learning, then it turns out the regret goes to square root of t, just like in the model-based paradigm. This shows these two paradigms are really commensurate here from the point of view of regret, if you do a reasonable job of exploration in the model-free paradigm. Okay, so I'm going to move on past that and move to the second part of the talk. So the first part was to sort of motivate why I have gotten interested in econ meets ML. And now the question is going to be, what can we bring to the econ side? What can we bring to the game theory and mechanism design literature that wasn't already there? And so the argument's going to be that what we've gotten good at in machine learning is dynamical systems and analyzing optimization algorithms, sampling algorithms, diffusions, and so on, understanding how fast they converge, doing that non-asymptotically, doing that in high dimensional spaces, and doing theory for all the above. So I'm going to mention now briefly a few kind of highlights of research that sort of summarized where not only my own group, but a number of related groups have come to over the last few years. And then by the end of the talk, I'm going to return to game theory problems and try to bring the dynamical systems perspective to bear, especially the non-asymptotic perspective to bear on some game theoretic problems. So let me start with a paper that really helped me and others to get going on this. This is going to be non-convex problems and saddle point. So in particular, we're going to try to avoid saddle points here because we were trying to analyze gradient descent. And so let me acknowledge again collaborators here, Chi Jen again, who was a student with me, who's now a professor at Princeton, Praneeth Netrapali, Rongu, and Sham Kakad. All right, so again, we're going to be reviewing a little bit of the connections between optimization and statistics and machine learning, especially in the non-convex setting. And so a conclusion of the last few decades of research has been the non-convex problems are particularly hard, not only for local minima reasons, but for saddle point reasons. In fact, you may have a few local minima in problems. You could have many, many more saddle points just for topological reasons. And so the question becomes, how can you avoid saddle points? You can ask questions about the asymptotic avoidance of saddle points, and we've had some work on that. But more importantly, how can you avoid saddle points non-asymptotically? How quickly can you get past the saddle points? Here's a picture of a saddle point in 3 dimensions, but you should think about a saddle point in 1,000,000 dimensions and be oriented in some arbitrary way, and it may have a very few number of directions which get you out. So you could be stuck for a long time before you actually get out. The question is how long, and what's the dependence on the dimensionality of the problem? That's where the deficiency is going to come to play. All right, so to briefly review, we're going to talk about gradient descent for the rest of this talk. And so here's gradient descent for this particular setting. We have a smooth convex problem in this picture. And you probably all know the gradient descent here will converge to a global minimum. And even more importantly, the number of iterations for convergence is independent of the dimension. So you can run gradient descent in infinite dimensions. It takes just as many iterations as in finite dimensions. That's already sort of an explanation, a partial explanation for why gradient descent is so special. But if you run gradient descent on this surface, a non-convex problem, there's all kinds of problems that are going to arise. You might converge to a local maximum. You might converge to a stationary point, which is not a minimum. It could be a saddle point. Or you could converge close to the saddle point for a long time so that it's not practical to get to the local minima. Okay, so let's talk a little bit about the theory here. This is the kind of classical analysis of, say, Nesterov in the 1990s. So under certain smoothness conditions, you can define a epsilon first order stationary point, meaning that the gradient nearly vanishes, and ask how many iterations do you need for that to occur, okay? So in the convex case, where there's only a single optimum, you will arrive at an epsilon ball of that optimum with the number of iterations, which scales as 1 over epsilon squared. So that is the rate. This is a non-asymptotic result. This is a bound on the number of iterations, and in the numerator, you see only a Lipschitz constant and initial distance to the optimum, and a 2. So this is a beautiful result. There's no dimension dependence, and it's a non-asymptotic result with no hidden constants. So this is the kind of thing we aim for in this field. All right, so what if we now go to the non-convex case? We're going to have now possible saddle points. So let's talk about second order stationarity, meaning the gradient vanishes or nearly vanishes, and you essentially have only positive eigenvalues. Okay, again, you give yourself a little bit of slop so that you can talk about a convergence rate. All right, so in that setting, we have analyzed a number of different algorithms. This is a particular result for something we call perturbed gradient descent. So it's gradient descent with a bit of stochasticity. The stochasticity is necessary. And we were able to prove that the convergence rate here is again 1 over epsilon squared, and prove that the numerator, show that the numerator only had a Lipschitz constant initial distance to the optimum, but also to show the dimension dependence. And it turned out to be polylogarithmic in the dimension. Okay, so it really is parallel to the convex case. We found now in the non-convex case, the number of iterations to arrive at a local minimum and move past all the saddle points is essentially the same as it is for gradient descent in a convex problem. All right. So I'm going to move past the kind of a little bit of the proof technique here. I just wanted to quickly allude to the notion that around a saddle point, there's some differential geometry which is needed, and you analyze essentially how thick a region is that has flow mostly towards the saddle point. And so this is kind of the high dimensional analysis one needs to do to get this polylogarithmic result. Okay, next part of this development was to start to ask questions about, are we done? That's a kind of a very pretty result. It's parallel to the convex case. We have a non-asymptotic result, or are we finished? In particular, we arrived at a result which is the best possible. We also want to know about what happens when we go to stochastic case and kind of talk about diffusions and so on. All right, so the next part of this talk then talks about the acceleration phenomenon, which, if you know about optimization in the deterministic setting, it gives you lower bounds on how fast you can go. And we'd like to see if we can understand the origins of these lower bounds, and then to extend them to problems that are non-convex and have other properties we're interested in. So this second part of the talk, I want to briefly allude to what's happened in this area. This is again work with some students at Berkeley, Andre Wibasona, Aisha Wilson, and then Mike Betancourt also worked with us on the symplectic geometry of this problem. So here we're going to be talking about dynamical systems, and particular physics kind of ideas, Hamiltonians and variational approaches to optimization. And I want to just say, make a sort of a provocative claim about sort of essentially the fundamental theorem of calculus. Fields that are very mature use both integrals and derivatives and go back and forth between the two. So certainly physics has this blend, and statistics does as well. Numerical disciplines like finite element analysis has both integral approaches to optimization and differential approaches. But I would argue that optimization in this sense is a little less mature. It's mostly derivatives. Derivatives, Hessians, gradients, and so on, and not much integrals. So I think this is something that's missing, and this line of work aimed to bring integral perspectives into optimization. All right, so let's return then to gradient descent and talk about this acceleration phenomenon, talk about what's the fastest you can go if you're trying to go down the hill and using only gradients. So again, this hopefully will be a review for many of you. For convex problems, if you run gradient descent, just like we've already alluded to, there's a certain convergence rate. I've written it down in terms of the number of iterations. It's 1 over k, where there's been k iterations. And there is a lower bound, which is 1 over k squared for this problem. And Nesterov discovered an algorithm which achieves that lower bound. It's called the Nesterov accelerated gradient method. Again, I'm not getting into details here, but hopefully you've seen this algorithm. It is a second order dynamical system. It's got 2 equations. There's the y term, which is effectively doing gradient descent, and there's an x term, which is a rotation of the last 2 y terms. So this algorithm is not a descent algorithm. It goes downhill, it goes back uphill, and in some sense builds up momentum and allows it to go faster. But it's been a bit of a mystery as to exactly why it goes faster, what it means to have momentum in a setting like this. And so we have argued, we and others have argued that you need real physics ideas to understand what's happening here. So gradient methods have been generalized to accelerated gradient methods. And so this is not only done for gradient ascent, but for a wide range of other gradient-based methods. All right, so on one slide, I'm going to show the result that we have in this paper, which is that we were able to find a variational characterization of acceleration methods, meaning that we're able to write down a energy functional, a Lagrangian, and we can derive in continuous time the acceleration methods for a wide range of acceleration methods. So they all have a certain differential equation that expresses them in a certain geometry, and that differential equation emerges just from calculus of variations. So the top of the page here is a Lagrangian. It is a time-varying Lagrangian. It has a Bregman divergence d sub h as its first term there. And we're going to argue this is something like a kinetic energy. It's a Bregman divergence, or a generalized distance between x and a time-scaled x dot. And then we subtract off the function f of x. Alpha, beta, and gamma are sort of degrees of freedoms. They're diffeomorphisms, which give you a space of algorithms and not just a single algorithm. All right, so that's a Lagrangian. It has a function h, which is the auxiliary function of the Bregman divergence, again, giving us a space of algorithms. And so if you put all those degrees together and you throw that into the calculus of variations, you go through the Euler-Lagrange equations, and at the bottom of the page, you get out a differential equation, which is optimizing those that variational problem. You can see it's a second-order differential equation. It has a damping term, and then it has a third term, which is sort of a geometric term. It has a Hessian of that h function. So this reduces to the continuous time version of Nesterov's algorithm. It reduces to a wide range of other accelerated algorithms. And there are some advantages to working in continuous time. In fact, I think it's essential to work in continuous time to really understand this acceleration phenomenon. So I'm going to argue here in a moment. One of the virtues of the continuous time framework is that you can get out a convergence rate once and for all in continuous time. Right? So it's just a little Lyapunov function argument. The continuous time framework also allows you to understand how this convergence relates to the geometry. So we really have a full kind of dynamical systems perspective here in continuous time. All right, now, so why did we go to continuous time? And, well, we got some limiting Lyapunov style arguments helping us out. But moreover, we have a more of a deeper understanding of acceleration. So it turns out that in continuous time, that you can go at any rate you want simply by changing the definition of time. So if someone's measuring time in a particular way, I can change time by a diffeomorphism and go at a faster rate. But if I do so, it turns out I'm going to follow the same path in the phase space. All right, so the geometry is determining what's the best path to follow, and the actual speed I move along the path is not so important. So these rates we've been talking about in the discrete time analyses classically in optimization theory, it's not really the rate which matters, it really is the path that matters. And we only see that in continuous time. Okay, so it is now becomes though a mystery why in continuous time you can go at any rate you want, whereas in discrete time you can't, because we have these lower bounds, these oracle lower bounds due to Nemirovsky and others. All right, and so it's going to turn out that the reasons you can go at a arbitrary rate of continuous time but not in discrete time is that the differential equation I showed you a minute ago can be discretized stably only for certain rates. And there's a phase transition which beyond which, if you try to go faster in continuous time, you're not going to be able to stably discretize the differential equation. Right? So it really has to do with a discretization of a differential equation. That is a way to understand acceleration. So again, if you're thinking geometrically, if you're following a certain path, at some point, the curvature of the path is too much and you can't discretize the differential equation. All right, so a way to get insight into this is to really take a more thoroughgoing understanding of the geometry and to think about the symplectic geometry of these flows that underlie optimization. All right, so we're going to be using symplectic geometry also to understand the game theoretic setting. So I want to pause for a moment and talk about it more directly. So symplectic integration is an idea that dates back for over 100 years. So Hamilton, Jacobi, Poincaré, some of the heroes of early dynamical systems research were interested in discretizing systems of differential equations. And they didn't have computers yet, but they were trying to understand more deeply how to think about Maxwell's equations and fluid flows and Newton's equations and so on. So they were interested in can I discretize these equations and solve them in discrete time while still maintaining invariant the underlying physics. So the physics will conserve quantities such as energy or momentum. And you'd like to ask, is it possible to discretize in a way that I still conserve those quantities exactly? And so symplectic integration is a perspective that allows you to do that. And so conceptually, instead of thinking of a vector field, and you're trying to discretize the flows in the vector field by just simply following a vector a certain distance and then continuing to do that, you should now think of a triple of vectors at every point. That defines a volume element. So via determinant, which is a polynomial. And as you move along the flow, that volume element will shear. And you'd like for the volume element to shear, but still maintain the same volume. So the volume should stay constant as you move along the vector field locally. And so since it's only a constraint on the determinant, it is a small number of degrees of freedom, you can actually find ways to do this. And that's what Hamilton, Jacobi, and others figured out how to do. Right, so why is this relevant to acceleration? Well, because if you're maintaining these volumes in phase space, you are finding a particularly stable way to discretize these differential equations. And because of the stability, it's possible to take a much larger step size than you would otherwise. In fact, this could be an order of magnitude bigger step size. And so that speed of discretizing, that fast movement in the discretization is the relationship to acceleration. Okay, so let me just show you a simulation first of all, before I say something about some theory. This is, we're now working with a Hamiltonian instead of a Lagrangian. You just simply do a Legendre transform to get from one to the other. And so you now start with a optimization functional. This was a high dimensional quadratic. You write down the Lagrangian I showed you earlier, or perhaps a Hamiltonian. You put that into an integrator, and that gives you an algorithm. And so here's that algorithm as it runs. It's going downhill, but going up and down, oscillating, building up momentum, and it's going down at the oracle rate. If you now compare that to Nesterov, this is on a different problem. You can see it's just as fast as Nesterov, but in fact, it's actually faster because if you turn up the step size, Nesterov will go unstable, whereas the symplectic integrator will still stay stable. Okay, so I want to now again briefly say something about the symplectic integrator and why that geometry is actually helping us here. Symplectic integration really arose. Hamilton and Jacobi were studying conserved systems, so systems that would oscillate. We're not interested in systems that oscillate. We're interested in systems that go downhill. So I'm going to talk about that in a moment. Let me just first of all just briefly mention putting these two ideas together. You can now ask, what about if I have saddle points in the problem and I'm doing acceleration? If I'm moving past a saddle point, is it helpful to have acceleration, or does it hurt to have acceleration? I might imagine acceleration takes me up the wrong side of the saddle point and I get to oscillations, or I might imagine saddle acceleration sort of moves me past the saddle point more quickly. And the framework that I've introduced allows you now to address this problem. So let me just sort of skip details here. Again, this is very much like the same setup before with our second order stationary points. I want to just mention that this Hamiltonian or Lagrangian perspective allows you not only to derive an algorithm, but also to do an analysis. So you structure the analysis by looking at the Hamiltonian and analyzing separate each term in the Hamiltonian. And that allows you to actually put together an entire non-asymptotic analysis. All right, so we did that in this particular paper, and I don't want to get into details again, but let me just mention the result at the top of the page, that the rate of convergence to second order stationary points, now we're again in the non-convex world, is epsilon to the 7/4, 1 over epsilon to the 7/4, which is faster than epsilon squared. So this is a proof that acceleration actually helps you with non-convex problems, not just the convex problems. All right, so enough on that. All right, so the last little the bit that I want to mention before I return to the symplectic problem is what happens when you put this together with stochastics. So what I've been talking about so far is optimization algorithms and differential equations. What if we talk about stochastic differential equations or diffusions? And so you can ask really interesting questions such as, is there a fastest diffusion? Is there a variational characterization of diffusions? If I want to diffuse down a hill towards a stationary distribution, is there a fastest way to arrive there? And this is not as common a line of research. In fact, I know very little on this. Diffusions are generally used to model nature, like in the Brownian motion, or to model financial markets. And it's less used by optimization or control people trying to to find a fastest diffusion. Okay, that kind of variational characterization. All right, so I want to again say a little bit about the research that we've been able to do in the last few years on this. The question is, how can you accelerate diffusions? And in fact, there have been negative results where you try to add an acceleration term to a diffusion and you don't get any bonus, or it even can get worse. And the reason is because most of this research is focused on overdamped diffusions. I'm going to say what that is here in a minute. So here is a diffusion at the top of the page there. It's a stochastic differential equation which has a gradient. It's a gradient-based diffusion. So it has a gradient plus Brownian motion. And if you analyze that, as has been done fairly recently, non-asymptotically, you will get rates of the form d over epsilon squared. So epsilon squared, again, appears just like back in the deterministic world. And the dimension dependence appears now, it's not independent of dimension, it's quite badly dependent on dimension, it's d. So this is really because the diffusion is kind of like a random walk, and it's seeing all of the ambient space around the path. All right. So instead of analyzing just that first order diffusion, if we're interested in faster algorithms, we imagine that it's appropriate to look at second order diffusions. So we have two equations now, not just one. And the gradient is now in the velocity term, as is the Brownian motion. So the overall paths now will be smoothed out by this second order equation. And we're also getting oscillatory behavior. So we might imagine you're able to go faster here. And it turns out the answer is yes, you are. So let me forget about the discretization. So here are rates of analysis of this algorithm. So it turns out to be not epsilon squared, but epsilon in the denominator. And even more interestingly, in the numerator, it's square root of d and not d. So somewhat surprisingly, even though it's still a diffusion, you're not seeing the entire ambient space in quite the same way. You're not paying a cost of dimensionality d in the numerator. It's square root of d. Okay, so last little bit before I return to the game theory setting and finish the talk. I want to say something about this recent work with Guy Franke and René Vidal, where we've actually been able to prove that this symplectic integrator gives you preserves the fast rates from continuous time to discrete time. Okay, and so to give you a sense of what we've done in this paper, this is a recent paper on the archive. I want to highlight the fact that there's a bit of a disconnect in what I've said so far. Hamiltonian dynamical systems were classically done for conservative systems that oscillate, have limit cycles, and conserve energy and momentum. Whereas in optimization, we're interested in dissipating energy. We're interested in converging to a point or perhaps converging to a distribution. And so how do we use Hamiltonian style ideas in the setting of dissipative systems? All right, so again, I don't want to get into details here, but I want to mention this line of work. What we've been able to do is to embed a dissipative system inside of a larger non-dissipative system, a conservative system, and run symplectic integrators on the larger system and then project back to the dissipative system. All right, so this is called gauge fixing in physics. And so all we've done is a particular gauge fixing for a symplectic manifold and projecting that onto a non-symplectic manifold. And that allows us to then use the kind of convergence results in particular backward error analysis that people use for symplectic integrators, use that in our dissipative problems. Okay, so here is a theorem at the bottom of the page here that we're able to actually show that the numerical or the discrete rate is the same as the continuous up to a small error, which we're able to quantify with a backward error analysis. All right, so that leads to a full-going theory that shows you when and how you can preserve continuous time rates in discrete time and control the error associated with that. All right, so the class of Hamiltonians we've done that for is shown at the top there. Our Bregman Hamiltonian or the Bregman Lagrangian from before fits into this overall framework. Okay, so that's all I wanted to say about that. I'm going to skip over this application of the Bregman dynamics. Here I've actually written out a full symplectic integrator just to show you that it can be done. You'll find that in that paper. Okay, so in the last 5 minutes, what I want to do is now return to game theory dynamics. This is work with Eric Mazumdar's a student with me at Berkeley. We're going to be interested in this particular paper in Nash equilibria, so saddle points. So I've highlighted this one because we already had saddle points in the talk. We have saddle points again. These are saddle points, however, in a different setting. These are in zero-sum games where you have a saddle point arising because one agent wants to go uphill, the other agent wants to go downhill. Okay, so in this case, saddle points are desirable outcomes. They are the equilibria you'd like to find under some kind of dynamics. So we're not trying to avoid saddle points, we're trying to find saddle points. All right, and the gradient-based methods that have been developed here have run into troubles, as you may know. Simultaneous gradient descent or gradient descent ascent, where you go downhill in one direction and then uphill, on one step and then uphill on the next step, can hit limit cycles. And they may not even converge. So there has been work focused on addressing this by adding terms to gradient descent. So you can get rid of the limit cycles. However, you have another problem, which is that Nash equilibria or game theoretic equilibria, in this case, are saddle points, but they're a special kind of saddle points. They're axis parallel. For one agent, you want to go uphill. For the other agent, you want to go downhill. If you tilt that saddle point, you're going to still have a saddle point, but it's no longer a Nash equilibrium. A gradient-based method is going to be blind to that. It will approach a tilted saddle point just as well as a Nash equilibrium and converge to something which is not a game theoretically desirable saddle point. Okay, so this now requires a geometry which takes into the fact that tilted saddle points are bad and axis parallel saddle points are good. Okay, so here's a little diagram, a picture on the left that shows you the problem. The green crosses there are saddle points, and they are actually also Nash equilibria. So gradient descent, ascent, as well as some of the algorithms that have been designed more recently to fix limit cycles all approach those Nash equilibria. But the blue star in the middle is a tilted saddle point. It's not a Nash equilibrium. And unfortunately, all of these algorithms approach that saddle point too. They're just gradient-based algorithms. They don't know any better. All right, so how do you fix this? Well, it turns out if you think about this gradient flow here, there is a symplectic component to this gradient flow. And here, whereas before symplectic geometry or the symplectic component of the vector field, which was what gave you acceleration, here it's actually the harmful part that's leading you to approach saddle points, which are not axis parallel. So if you subtract away the symplectic component, and that's what this algorithm does here, which we call LSS, local symplectic surgery, it is taking the gradient flow and subtracting off, canceling the symplectic component. Then you have an algorithm which will provably converge to only Nash equilibria, and only Nash equilibria. So again, it doesn't have saddle points, and moreover, it doesn't converge to tilted saddle points. So it only converges to Nash equilibria. So you can see that in the picture on the right there. The red dashed line is the new algorithm, which in the middle of the diagram is approaching a non-Nash equilibrium saddle point. But once it's in the neighborhood, it sniffs out the eigenvalue structure, realizes that it shouldn't converge, and it moves to a nearby saddle point. Okay, so that's what I wanted to say about that. Let me just mention in the last few minutes another line of work which is related to what I've been saying. This is applying diffusions back to the bandit problems we had earlier. Again, this is with Eric and some other colleagues at Berkeley. And the goal here is to be able to design algorithms which diffuse quickly or do gradient descent quickly enough that you can actually still have good regret bounds in bandit algorithms, right? So classical work on bandit algorithms were done with these extremely simplified algorithms, and the proofs were based on things like upper confidence bounds. But if you see the applications of bandits in industry and in real life, often they are more complex. They are often Bayesian. They involve things like Thompson sampling, where you form prior distributions and posterior distributions for selections of arms. And here you now have to have an update algorithm, which is a Bayesian update that takes a prior into posterior and updates that as you get experience with the arms. And Bayesian updates are notorious for being asymptotic. We don't have typically non-asymptotic rates of convergence for Bayesian algorithms. And so it's hard to put them in something like a regret bound for a multi-arm bandit. You may wait too long and you may lose your good regret bound. So by taking some of the technology we've been developing in the rest of the talk, we're able to show that there are classes of algorithms which are Langevin based that are fast enough that they converge in the context of a bandit algorithm and still give you things like logarithmic regret. Okay, so I don't want to get into details here. You can see the paper on the archive. They're basically using novel posterior contraction rates that are Bayesian, so conditional posterior contractions that take advantage of this Langevin framework. Okay, so I'm going to skip these slides here at the end and move all the way to the conclusions. All right, so I'm going to finish with a slide I already had up earlier. I've emphasized in this talk that decision making is equally important as pattern recognition in real-world applications of machine learning, especially when you have high stakes decisions and you have uncertainty, you have sequence of decisions and so on. And so I really think this is the beginning of the era of decision making, returning to an earlier era, and in the context of pattern recognition. So high dimensional spaces, large numbers of alternatives, and so on. And in doing so, I want to particularly emphasize the fact that this requires consideration of game theoretic and market design and market mechanism design sorts of ideas blended with machine learning. Okay, so hopefully that was of interest to you. In fact, let me skip that last slide and stop the share, and I'm happy to take questions if there are any.
Yes, if folks have questions, feel free to either type it in the chat and then I can read it out, or if you would like to jump in, go ahead. Well, if there are no questions, I can ask at least one. So at the beginning, you talked a little bit about some of the things that you've done in industry, and maybe this is a little bit of a trite question in some sense, but what role do you see industry playing in this sort of new space? They have the ability to scale and deploy things, but oftentimes their discoveries are really driven by business interest, and so maybe that doesn't align with sort of the academic perspective. So yeah, I'm curious what your thoughts on how to engage and interact in a way that's fruitful for both sides.
Yeah, so I think again it's helpful to distinguish pattern recognition and decision making. So deep networks and neural nets and all that at really huge scale, people have emphasized that that industry can do that and academics can't, and I don't really buy that. So for many of the real world problems involving neural nets and pattern recognition, you don't actually need the big data sets and you don't actually need the huge numbers of machines. Your problem is often a little bit smaller. And some of these really large architectures, like for vision or natural language, are commodities. You can download them and use them, but your problem doesn't require all of that. So I think that academics and smaller companies and so on are absolutely able to use the pattern recognition technology of the era. And in fact, the data you need for any given problem, probably Google or Microsoft or whatever doesn't have it. You have it, okay? Now, on the other hand, decision-making problems often involve decision makers in closed loop systems where there's all kinds of options and there's money involved and there's goods and products and markets. And we can't create that as academics easily. Amazon has that, Alibaba has that, and so on. So I think actually that's where going into industry and spending time and talking and working on those problems gives you perspective on what are real market making and decision oriented problems involving real customers and producers and consumers. And I think it's still a very large gap to being able to make benchmarks and to be able to actually have systems that all of us can work on. But that's also true in industry. You can't, inside of industry, try out your new algorithm on the Amazon platform immediately. And so, they have simulators and they, do all kinds of A/B tests and so on and so forth. But I think there's going to now have to be quite a big effort to make really viable simulators and other kind of benchmarks so that we can try out control problems and market design problems and so on at scale for interesting classes of problems. I mean, this certainly happened in the control theory literature. You did not design airplanes by simply trying them out in airplanes. You had simulators, and that drove research for a long, long time. So it's partly industry and the perspective of the new problems that emerged there. I think the problems that Alibaba and Amazon solve are actually fascinating. They really are about producer-consumer relationships. But to actually work on them as academics, we're going to have to either borrow the simulators. It's not just to have enough to have the data. You can try to get data from them. They're probably not going to give it to you, but it's not that valuable. It has to be about the whole closed loop systems.
Yeah.
So that's where I think the perspective is particularly interesting. It's on the decision-making side.
Yeah, that makes sense. So there's a question, raised hand. Here's Sam Burden, if you want
to. Okay, super. Can you hear me okay?
Yeah.
So I'm an assistant professor here in ECE, but also a Berkeley alum. In the words of my advisor, that talk was a real tour de force. Thank you very much. And in particular, I'm coming from the control theory side, dynamical systems kind of perspective, and I've dabbled or collaborated with Lillian in game applications in game theory. And I'd be really excited to hear your thoughts on how to train the next generation, starting from the undergrad level and the grad level, at this novel interdisciplinary intersection. What kind of new classes should we be teaching? What kinds of new undergraduate labs should we be putting together? I'd love to hear your thoughts.
Okay, yeah, no, I got a great question. Thanks for that question. I got a great answer to that, the undergrad part. Grad, I don't have such a great answer. But actually, I spent 5 years helping develop or leading the development of some new classes at Berkeley. That's a whole curriculum at the undergrad level. And so we use the data science mantra here because we were trying to have an umbrella terminology, but really it was a lot of statistics, a lot of computation, a lot of control theory, all kind of blended together. And we started at the freshman level. So it's now a very famous class. It's called Data 8, and it's taken by thousands of people at Berkeley every year. So it teaches them Python meets statistical inference meets decision making and real data, and students love it. It's really popular, very widely taken across the campus. That leads then into a second tier class. It leads into a new version of a probability class. And then the capstone class is a senior level class that I've been teaching where we have bandits and matching markets and control theory and false discovery rate and all sorts of fairness, privacy, differential privacy, all kind of blended together in a computing oriented mix. So I've really enjoyed, with my colleagues working out this new curriculum. We wrote a paper that's now going to be a discussion paper in the Harvard Data Science Review. And we put that up a couple of months ago. It's called on computational thinking and inferential thinking, blending, something like that, blending curriculum at Berkeley. Anyway, you'll find that on my website. I am as proud about that as any of the research things I've done. I really enjoyed trying to work. I think if the ideas are good enough and powerful enough, you can teach them at the undergrad level. And so it's been really the interesting challenge, and I think it's really worked out. At the grad level, it's a whole nother story. I think there in my own research group, we'll spend a few months on a mechanism design book, a few months on a control book, a few months on a PDE book, a few months on stochastic visualization. We just keep hopping around and sort of assume, problem focused, but assembling the right tools, and not trying to ever kind of stick in one framework, trying to always pull them together. And in some ways, the right way to learn is kind of the Wikipedia way. You know about, I don't know, Grunwald's equality. You go to a Wikipedia page, you learn about it, you use it. You keep moving around. I don't think I have a better idea for grad education at present.
Yeah. Okay, I think we're basically past the time. And so unless there's any pressing questions, I think we'll conclude. And thank you very much, Mike, for giving this wonderful talk.
All right, I appreciate having a wonderful audience. I appreciate it. Take care, everyone.
Thank you.